Hello, everyone. Welcome to the webinar titled Advanced Air Distribution Design. My name is Mike Kuprianov, and together with Sandrine, we're going to be your presenters for this webinar. So I'm going to first introduce myself, and then Sandrine can introduce herself. So my name is Mike. I'm a manager at Price Industries, and I oversee the CFD and energy modeling team at Price. And my team and I have consulted on over 200 projects using CFD over the last 10 years. I'm also a regular presenter at ASHRAE conferences, and I'm also very active on the various committees.
Hi, I'm Sandrine. I've graduated from the University of Manitoba in mechanical engineering, and since I've graduated from the university, I've been working with Price Industries, specifically in the grills, registers, and diffusers application department. What I do day in, day out is help people select a diffuser for their layout and really explain to our clients how to use our GRD products to create a comfortable environment. In this presentation today, I'll be discussing a lot of challenging spaces that typically come up and how to condition these spaces to create a good comfort. So handing it off to Mike to go over the course summary.
Thank you, Sandrine. So just as a summary of the course, because diffuser selections are not always straightforward, especially in challenging areas like tall or wide spaces, we're going to present to you a couple of case studies where we'll be specifically looking at kind of these types of more complicated examples. And we're going to use CFD throughout the presentation to basically assess the designs. As well as we'll have a short section at the beginning to discuss kind of what CFD is and how it can be used to validate the various complicated projects. So these are the learning objectives, mainly to understand where to use CFD and the benefits, understand the challenges associated with tall and wide open spaces, understand how heated and cooled air can affect diffuser performance, as well as strategies that can be used to minimize any type of concerns with performance, as well as to understand how air travels in a displacement system in both heating and cooling type of applications. So this is the agenda of what we're going to talk about. I myself am going to start on point 1, present to you what CFD is and where we could use it. I will then pass it off to Sandrine for the following 3 case studies looking at the hospital patient room, a heating and cooling application in a tall space, as well as an art gallery. And then towards the end of the presentation, I'm going to be talking about an auditorium case study. This is looking at displacement ventilation. So we're going to start first by diving into what CFD is. And first, I'm going to define it for anyone who doesn't know what it is. So essentially CFD, which stands for Computational Fluid Dynamics, it's basically an analysis tool that we can use to predict the performance of an HVAC system in the indoor environment. So essentially what we're predicting is things like airflow patterns, temperatures, thermal comfort, indoor air quality, or even the movement of contaminants within the indoor environment. And I like to kind of contrast CFD a little bit with energy modeling, since a lot of engineers are more familiar with energy modeling. So typically in an energy modeling, you might look at the system in the whole building to figure out energy usage, control strategies, and such. In CFD, it's a little bit different because typically you would only apply to a single strategic or difficult to design space within a building. Another really good use of it is for a space that repeats many times throughout a building, like maybe a private office or a patient room. So as you can see in the picture here, it's this really beautiful, picturesque looking building. It has a very complicated atrium. So in this case, that would be the perfect application for CFD. So in terms of where CFD gives you the best bang for the buck, I like to break it up into 2 broad categories. So the first one is high risk environments, and the other one is challenging applications. So in terms of high-risk environments, I'm talking about hospital spaces, so whether it's operating rooms, patient rooms, or any other type of exam rooms within the hospital building. Other great applications are any kind of clean spaces where you need cleanliness in the air, specifically compounding pharmacies, labs, either with or without fume hoods, or any type of specialized manufacturing spaces, whether we're talking about pharmaceutical manufacturing or perhaps electronics manufacturing, both of which need very clean air and very low particle counts, and CFD is a great tool to verify that. As well as it can be used in horticultural applications to optimize product yields, ensure that the environment that we get is meeting the criteria of the plants that are in that environment. And finally, in industrial applications as well, not as much for comfort, but mainly looking at better air quality for the workers. Challenging applications, so this would be what I would like to call your architecturally complex spaces, so spaces with high ceilings or no ceiling, any type of large open spaces, auditoriums, atriums, ballrooms. Really anytime you have a large glass facade or a curtain wall, or if you have extreme heat gain or heat loss, which tends to go hand in hand with a large glass facade. And then finally, just to kind of tie off the CFD intro section, the main benefits of CFD for the design engineer is it's a great way to mitigate design risk. And the way that that works is that because you're not only using it to validate how well your design works in terms of comfort and air quality that's delivered, but also it can be a way to verify load calculations specifically for the larger, more complicated type of spaces. And also that opens up opportunities to downsize the mechanical system because you're verifying your loads. So in a lot of cases, particularly with engineered systems like displacement, you might see that the CFD shows you that you don't need quite as much air as you think. So that could actually lead to cost savings and better energy efficiency. And finally, it's a great value engineering tool to kind of optimize each project dollar upfront, and also a good way to catch costly design mistakes before anything gets built. Now I'm going to pass it off to Sandrine.
Thank you, Mike. So in the next few slides, I'm going to be going over some of these challenging spaces that Mike referenced earlier on. Some of these specific cases are hospital patient rooms. There's a number of different challenges that come with designing a hospital patient room. The first one being the small footprint. Typically in these patient rooms, we don't have a large area, so we want to be selecting a diffuser that doesn't cause any drafts. We don't want to select a diffuser that has too long of a throw so that the patient is uncomfortable. There's typically a lot of hard surfaces in these patient rooms, so there's not a lot of sound attenuation. We're most likely not getting that 10 dB room absorption rate that we typically would see in office spaces. So here we want to make sure that we're selecting a diffuser that is quieter than your typical spaces. We also typically can have some obstructions in a patient room, such as a bulkhead, current overhead rails, anything that can disrupt your airflow pattern and change the horizontal pattern of your diffuser to more a vertical pattern, which could cause drafts in the occupied zones. So just really thinking about these obstructions when we're placing our diffuser. Another challenge with a hospital patient room can be high solar loads. A lot of patient rooms can have windows, which can have an impact on the comfort of the room itself if it has some large loads. And last but not least, the patient with low clo. A lot of times the patient in these hospital beds might not have a lot of clothing. They might have a lot of exposed skins. So we want to make sure that we're reducing the drafts in that occupied zone to make sure that they're not uncomfortable. So how can we do this? Or what is a common misapplication for this space? What we typically see designed for these small spaces is a radial diffuser installed right over the patient bed in the middle of the room. The rationale behind this is that a radial pattern diffuser will typically have shorter throws and low sound. So although it sounds ideal for a patient room, typically it's not recommended because it can cause some drafts right over the patient. So here's a radial pattern diffuser, a square plaque diffuser installed in the center of a patient room. And we can see that what happens here is the air is going to hit the wall at a high velocity and travel downwards onto the patient bed. Because the patient bed is directly against the wall, the patient is more likely to see some high velocities. So the patient is most likely going to feel some drafts and be uncomfortable if you have a radial pattern that's hitting that wall at a high velocity. So where should the diffuser be placed, and what type of diffuser should be used in this circumstance? This question was posed by one of our clients that had a small footprint hospital room. Their baseline design was a double pane window with a ceiling perimeter radiant heat. They wanted to know if that radiant heat was really necessary to condition the window, or if a single diffuser or maybe two diffusers could condition the space as well as the window. So we came up with two different alternatives to see if we could condition the room with just diffusers. So the first alternative was a triple pane glazing window with a three-way diffuser. And the second alternative was a triple pane glazing window with a two-way diffuser this time and a linear slot at the window to help and condition and wash that window. Some of the things that we can see in the room here is that there is a curtain. So we do have some obstructions. We want to make sure that the air is going to be able to go over the curtain. We've got our patient in our bed as well as another occupant. And what we can't see here is that there's actually a couch right under the window. So we want to make sure that the velocities both at the patient bed and at the window are not too high to create discomfort. So instead of doing CFD on this room, because it was a smaller space, we were able to do a mock-up of the room. So we can see up top, we have our slot diffuser, which is going to be used in the second alternative, the second case, and our ceiling diffuser right above the patient bed, closer to the wall here in a three-way pattern for first case study. There's also our sensor tree, which records the velocity and the temperature at different heights. So we can see if the temperature will be close to the set point temperature, and we can see what the velocities will be to ensure that there's not any drafts right at the patient bed. We also have our human body simulators. These give out the same amount of heat as a human would, so are there to mimic humans. We also have our window at the back, and this is going to be set to the required outdoor air temperature. In this case, because it was in heating, the window temperature was cooler to see if the heated air from the diffusers would be able to condition the window. So here is our first case, our first alternative with a three-way diffuser at 250 CFM. The room set point was 74 degrees and the supply air temperature was 79 degrees. We can see that unlike the radial diffuser, the air isn't dropping directly on the patient. It's going along the ceiling and then down the wall to create proper mixing. The velocity that's getting towards the patient is much lower than it would be with a radial ceiling diffuser. We could also see that the air was making it over the curtain and would be able to condition the window even when the curtains were closed. So here are the test results. We placed the sensor tree both at the window and ran the test, and then tested it at the patient bed. We can see that the head to toe temperature here is all within 1 degree Fahrenheit. And ASHRAE recommends a maximum head to toe temperature differential of 5 degrees. So we're well within the ASHRAE recommended range. We can also see that the velocities, both at the window and at the patient bed, are not too high, although ideally we would want the velocities in the occupied zone to be closer to 30 foot per minute. There's a few spaces near the window where we're exceeding that 30 feet per minute velocity. But all in all, the hot air is doing a good job at conditioning the room, both at the window and at the patient. So let's see now what happens when, instead of using a 3-way diffuser, we use a 2-way diffuser, as well as a linear slot diffuser. Here we still have that 250 CFM, but we've just split it between our ceiling diffuser and our slot diffuser. We have again the same room set point and supply temperature. We can see that the corner diffuser does a good job at conditioning the interior spaces, while the slot diffuser does a good job at conditioning just the area around the window. Again, just the video. Here we can see the slot diffuser, the smoke coming out, conditioning the window area. So what were the test results like for this second alternative? We can see that the head to toe temperature for both the window and the bed, instead of being 1 degree differential, is more around 2 degree differential, but again, that's well within the ASHRAE recommended range. We also noticed that the velocity are much lower in the occupied zone. We're not seeing those higher 50 to 40 feet per minute velocities in the occupied zone. So this will be less likely to cause drafts. We do see that at the window, at the 108 inches off the floor, we're seeing some higher velocity of 79, but since this isn't in the occupied zone, it shouldn't be an issue. And it is expected, as we had a slot diffuser in the ceiling, so we're getting that high velocity from that slot diffuser. So what are our main takeaways from this patient room? So based on our mock-up testing, it was decided that the radiant panels were not needed. They were not worth the cost, and both the first and second alternative did a good job at conditioning the space. Although it was decided that the second alternative was more comfortable, so we would typically recommend this layout. It did a better job at satisfying the heating loads at the facade, so it's doing a better job really at conditioning the window, and we had lower velocities throughout the occupied zone. So really the takeaway here is that a radial slot diffuser might not be your best option. Going with a modular diffuser with directional throw might be a better way to condition your space. In the next few sections, I'm going to be going over some of the most challenging spaces to design, which are tall open spaces, like Mike mentioned, atriums, lobbies, airports, auditoriums, or halls. These are all tall spaces, and they have multiple challenges associated with them. Although they all have similar challenges, no two job is the same. So all the challenges are slightly different going from one to the other. So in the next few slides, we'll be going over some of these different challenges. So some of the challenges with these tall, large spaces is getting the conditioned air into the occupied zone. Typically, these spaces can have multiple floors with mezzanine, so that also need to be conditioned. So we're not just conditioning the lobby, we might have some secondary or third level spaces that we also need to condition. We want to get a full coverage of the space. There can be areas with overhangs, and making sure that these are also conditioned so that we don't have any dead spots. Again, just comfort in the occupied zone. It's one thing to bring the air down into the occupied zone, but making sure that people are comfortable and that we're not creating drafts or that the space isn't too stuffy. These spaces can be highly architectural, which typically means hiding our diffusers, which comes with this own set of challenges. And last but not least, dealing with heating and cooling differences. The throw variation between cooling and heating can be really large, and sometimes it's hard to find the correct compromise between the heating and cooling throw differences. So as I said, although all of these tall spaces are similar, no two jobs are the same, and there's often multiple ways to address these challenges. In a lot of cases, displacement is used to condition these large spaces, but you can also use mixing to successfully condition these spaces. So throughout the next examples, I'll be going through different mixing systems, and once I pass it on over, it will be Mike with a displacement system. So diving right into our first example, which is a large boardroom in Virginia. This boardroom has a very large footprint and has about 50 occupants. The boardroom also has some very tall ceilings, 20 to 26 feet ceiling. There was some different elevations in there. It has a large exterior wall made of windows. So again, some solar loads that we're going to have to condition. And there was also an AV screen on the other side. So just getting an idea of the layout of this boardroom and the characteristic of this job. We had a room set point temperature of 74 degrees Fahrenheit. In heating, we had about 1,700 CFM at 75 degrees Fahrenheit. And in cooling, we had about 3,000 CFM at 58 degrees Fahrenheit. So in this room, we had a lot of different features. We had some curved ceiling diffusers, some high sidewall diffusers, as well as some baseboard heaters to help and condition those windows. The main challenges with this space was really to get proper mixing in both heating and cooling with these tall ceilings. We also couldn't necessarily place a diffuser right along the windows to condition the windows because there was a beam located halfway down the exterior, halfway down the wall. And then the air would hit this beam, detach from the windows and drop into the occupied zone, creating drafts. There is also a cloud ceiling. So you can see that there's different elevations here in this boardroom. So making sure that the air was going to be able to bypass that cloud ceiling and make it into the occupied zone. And again, this was a very architectural space. So making sure that the diffusers were hidden was part of this project. The preferred location for the diffusers was hidden above the cloud ceiling, as shown here. But after doing some analysis, we found that the optimized location was actually to place the diffusers in the cloud ceiling instead. For the specific layout, we did 4 different case studies. Between all of the different case studies, we were changing the diffuser placement, the number and size of slots, the temperature, the supply temperatures, as well at the end, some minor pattern adjustments. The main changes here are really that case 1 and 2, the diffusers were hidden, like it was shown in the previous slides, so above that floating cloud. And in cases 3 and 4, the diffusers were placed in that floating cloud instead, closer to that occupied zone. And then finally, we can see that between case 4 and 5, there was no change in diffuser placement or any adjustments like that. It was just really that the case 4A was a BEB system with lower supply air temperatures and cooling. So let's take a look at the first case layout. We can see here that there's diffusers along the window in this box. Here, these diffusers were hidden along with the diffusers on the opposite end of the room. And then again, we had some high sidewall diffusers. You'll also notice that these diffusers were used for both supply and return. So they were alternating supply and return along the lengths. So let's take a closer look at that first case and what prompted the changes. So at first glance, the temperature contour doesn't look that bad. There is some stratification. It's not necessarily at that 74-degree set point, but in the occupied zone, it is fairly close. So why did we have to change the diffuser placement? Why was there so many cases? When we start to look at the velocity streamlines, we can see that we have some issue. The air isn't making it in the occupied zone. Because that air was so hot and so buoyant, it wasn't making it all the way down and conditioning really that occupied zone. It was stopping short and then going back up into the returns. We can really see this when we take a look at the ventilation effectiveness for that first case. We're really not effectively removing the contaminants. In an ideal mixing system, the ventilation effectiveness in the breathing zone, or really in all zones, would be around 1. So it's fully mixed, there's the same amount of contaminants at the supply than at the returns. But as we're seeing here, the ventilation effectiveness is more around that 0.3, 0.6. In fact, for the first case in heating, we were really not properly mixing the air. And this prompted us to make all of the changes to get to case 4, where we're getting a ventilation effectiveness of 1.06. So what changes did we make? And really we made the changes based on the heating case, because as we can see in the cooling, the ventilation effectiveness in cooling in case 1 was already very good. We were already getting the air into the occupied zone. So comparing the velocity streamlines between case 1 and case 4, the first thing we can notice is that the diffusers were lowered down. So those hidden diffusers were lowered into that cloud ceiling closer to the occupied zone, so the heated air didn't have as far to travel before hitting that occupied zone. The same can be said with those sidewall diffusers. The next thing we did is add some low-level returns. These low-level returns really help mix the air and bring better ventilation effectiveness. So not all of the air is being returned at the ceiling, some of it is at the floor level as well. And lastly, what we did is we changed the supply air temperature closer to the set point. So instead of being 78 degree Fahrenheit, it's 75 degree Fahrenheit. Keeping the heated air temperature closer to the room set point temperature makes it easier for the air to travel into the occupied zone. There's less of a buoyancy difference between the heated air and the room air. So now that we made all of these changes and optimized it for heating, what about the cooling? Are we going to be creating some uncomfortable drafts in cooling, or is there going to be cold spots in cooling? So if we compare the temperature contours from case 1 to case 4 in cooling, we can see that although we had good ventilation effectiveness in case 1, it also wasn't the ideal scenario. We can see that there's some hot spots near the window, and there's also a cold spot right here at the ceiling, where it looks like the air was almost getting trapped between the ceiling and the cloud ceiling, so not necessarily making it down into the occupied zone. When we're looking at case 4, there's definitely some stratification, but it's not in the occupied zone, so we're not as concerned with it. There are some areas of temperature lower than the room set point temperature, but really this was deemed acceptable. When you're designing with a mixing system for both heating and cooling, there's always a little bit of compromise. You can either do your best to have the perfect system in heating, the perfect system in cooling, or try to make sure that in both cases, most people are relatively comfortable. And after doing these case studies, it was decided that most people would be comfortable in both heating and cooling with these changes. So what did we learn from this tall boardroom? The first thing that we learned is to keep the temperature differential between your supply air and the room air to a minimum, especially in heating when it's a little bit harder to get the hot air down into the occupied zone because of the buoyancy effects that shorten the throws in heating. We also learned that low sidewall returns can help bring the air down in heating, so less stratification. And finally, just bringing the diffusers down into the space can help the air reach the occupied zone better. So although ideally the diffusers would have been hidden, in this case it was just not possible, and it was deemed acceptable to hang the diffusers in that cloud ceiling. So those are really the key takeaway points from this case study. The last space we're going to be taking a look at is, again, a large open space, and this is the lobby of an art gallery. So in this case, we were asked to do the CFD on both the lobby and some of the galleries, but for the sake of this presentation, I'm only going to be looking at the lobby. This lobby has 2 floors, including a mezzanine that needs to be conditioned, and tall 27 feet ceiling. Again, it has a large footprint, and this is located in California, so we're only going to be looking at cooling. There's also some solar loads at the entry points, but these are minimal. And unlike the previous project where we had multiple cases, this one was just a baseline design. The client wanted to see how their design would work, and then based on our CFD and our recommendation, they were able to make the changes and not get another CFD analysis. So looking at the lobby here, again, we've got the room set point at 74. The cooling is about 11,000 CFM at 56 degrees Celsius, or Fahrenheit, sorry, to condition both the lobby and the mezzanine. Here, we wanted to use only slot diffusers, again, for the supply and the return. We can see all of the supplies are in orange here, mostly in the ceiling, some additional slot diffusers on the second level on the ceiling of the mezzanine, and then the return opposite in yellow. So what were the challenges with this space? The first challenge was that it was 2 floors with some changes in elevation. So we had some covered spaces like the entryways, but we also had some large open spaces like the main lobby area. It was also an architectural space, and they only wanted linear slot diffusers. So that really reduces the options that we have for diffuser selection. And finally, there was a large temperature differential between the supply air temperature and the room air temperature. So diving in and looking at some of the temperature contours for this lobby space. Here we've got some side views of the lobby as well as a plan view. The temperature set point was 74. And we can see here the slot diffusers as well as their location in the plan view. So if we take a closer look at that scale, we can tell that everything is well below the set point of 74. Everything is more or less in green or blue, so under 71 degrees Fahrenheit. That means, or we're assuming that the supply air system is oversized for the assumed loads. So this is something that we can minimize the supply air system. We could reduce the temperature differential because the loads were not as large as we thought they would be. We can also see that there's some cold spots, specifically at the enclosed spaces that have dedicated slots. Here, again, reducing that temperature differential between the room air or the set point and the supply air would help to minimize those cold spots. And also for some of these entryways, instead of having a one-way horizontal diffuser, maybe having a two-way horizontal diffuser, some of the air pointing towards the lobby would help and mitigate some of those cold spots. So we already know that the temperature contour was had some cold spots in there. What about the velocity? So we can see that we have some high velocity spots in the occupied zone, specifically here where we see some red spots, also shown by the arrow on the left-hand side. Typically, ASHRAE recommends 30 feet per minute in the occupied zone. We're seeing about 100 feet per minute. What we could do here, again, is to reduce the temperature differential between the supply diffuser and the room air. That's going to reduce the velocity of the cold air. So the air making it into the occupied zone should be coming in at a lower velocity. For the areas on the left-hand side, right against the wall, we do see some higher velocity areas, but because this is against the wall, it's not as concerning because we're assuming that people aren't necessarily spending a lot of time right against that wall. When we study that velocity streamline design a little bit closer, we can see that a lot of the air is going straight into the mezzanine area, when really those high ceiling slot diffusers were intended to be conditioning the lobby area. So instead of conditioning the lobby, we're just bringing a lot of air into the mezzanine. That's reflected in our contaminant removal effectiveness, in our ventilation effectiveness. We can see that in the lobby area, it's a lot more yellow than green, so we're not doing as well of a job to removing those contaminants. So what we could do here is bring the diffusers on the left and the right hand side closer together, centered more into the lobby area, so that the air would be conditioning the lobby more than the mezzanine area. And the last section we want to be looking at for this job is the entryways. At first glance, it looks good. It doesn't look like we have excessive velocities in the occupied zone. But if we zoom in on the entryway on the right-hand side, we can see that what's happening here is we're actually short-circuiting that supply air directly into that return slot, so that supply air isn't making it into the occupied zone, isn't making it into the lobby, it's going straight into the return. So here, what we would want to do is, instead of having supply on one side and return on the other side, it might be better to alternate the supply and the return just in one straight line, like we saw in that boardroom case. That should help mix the air in this zone. Alternatively, if they had allowed for other styles of return, using a low sidewall return again would help and bring the air down into the space and would do a better job at mixing those entryway points. So what were our recommendations for this art gallery? So our first recommendation was to move the ceiling diffusers, those 20 diffusers that were conditioning the mezzanine, closer together to improve the contaminant effectiveness. So really to just condition the lobby more than the mezzanine. We also recommended to change the return location in the entryway, some low sidewall returns, or to alternate the supply slot diffuser to be supply and return. And last but not least, to decrease the temperature differential between the supply and room air. We know that our system was oversized and that the temperature differential was creating some drafts. So bringing that supply air temperature closer to the room air temperature would help for both of these. So this really wraps up how to condition some of those tall and large spaces using a mixing system. And now Mike is going to be going over how to condition these systems using displacement instead.
Thank you, Sandrine. So the case study that I'm going to be looking at is going to be an auditorium. So strangely enough, it is also located in California. In terms of size and layout, I guess it's kind of got that typical pie shape that you would see in a lot of auditorium designs. It's got a high ceiling of about roughly 18 to 20 feet. Kind of this weird ceiling thing that you're seeing in there. I'm sure that's not typical, but I'm sure that every auditorium has at least one or two strange architectural features. And the occupancy in this case is just over 300 occupants. Now, one of the things that makes this one a little bit more unique than a typical auditorium is that mostly they're interior spaces. So all the walls are interior walls, but in this case, we actually have two exterior walls with windows, and they're east and west facing to boot. which is a little bit of foreshadowing to say that there's going to be some solar load that we will have to deal with. In terms of the rough dimensions that I want to point out, kind of at the narrowest point, the auditorium is just under 50 feet across, and at the widest point at the back, it's just about 65 feet across, and that's going to become important when we're looking at the displacement diffusers that we want to put there. So in terms of the air distribution strategy, I kind of have a mechanical drawing with some things highlighted on there. Now in this case, we don't have the luxury of having an underfloor plenum where we can put a diffuser next to every seat or every other seat. So in this case, we're doing something that's done quite commonly, and that's having displacement diffusers on the side walls. And this is where the distances across become important, because depending on kind of the density of the space or how much stuff is in there and how much thermal loading there is a limited amount of distance that that displacement diffuser is going to be able to cover. So I think the typical rule of thumb is about 30 feet, but again, that depends on loading and how much stuff that air has to pass through. In this case, we have some diffusers around the back as well to kind of fill in the air for the wider portion of the auditorium, as well as we have some displacement diffusers on the stage as well. Now, because we're going to be looking at cooling and heating, or I guess I'll call it heating light because it's in California and we're presenting from Canada, so this is kind of very mild heating from our perspective. In this case, we're going to use trough heaters on the windowsills to kind of provide warm air and wash the windows with warm air to provide the heating. And as in any good displacement, we have returns up high in the ceiling, right? In any displacement system, you want your returns as high as possible. So looking at some of the loads for the auditorium, nothing crazy. The total cooling load is just under 150,000 BTUs. A lot of that coming from occupants and the equipment. Now, the equipment in this case, we're assuming is that everybody basically has a laptop. So I guess kind of like a modern auditorium where everyone's got some sort of a computer. That's people on the stage and in the audience, as well as a projector. Solar load is not too bad. These windows have pretty good shading, but you can see that's included in the model. In this case, outdoor air temperature is quite warm, and we're using a 65-degree air temperature for our supply air in displacement, which is kind of the sweet spot for what you want to do. Total air volume is just under 10,000 CFM, and in heating, because again, the outdoor temperature is pretty mild, about 30 degrees Fahrenheit, the heating load is just over 15,000 BTUs of heat loss, which is what we're going to be using our trough heaters for. So we're going to be looking at two different design options. Now, when we worked on this project, we looked at quite a bit more, but just for the sake of time, I've kind of distilled it down to a design A and design B. And again, because just to make the comparison simple, because the loads are the same, we're using the same air volume and the same supplier temperature. Really, the difference between these two examples is the diffuser layout. So the sidewall diffusers are the same in both cases. Really what differs is how we supply air at the back and from the stage. So in the first case, we're actually using grills on the top of the windowsill. The intent in that case was to actually not use a trough heater in design A, but just to supply cold or hot air. And it's really in design B where we went away from that and just put in kind of a dedicated system, with the additional advantage being is that you're not using any additional air to do that heating. So these are the different diffusers that we're using, the different sizes, the counts, as well as the air volumes. And hopefully you can orient yourself around the CFD models. I've tried to point out exactly where these diffusers are located. So let's dive right into the results. The first thing we're going to look at is cooling. Looking at design A, I have two plots that I'm showing you. One is a temperature contour kind of looking above the floor, and the other one is planes cutting through the center of the space. The main reason I'm showing that is twofold. So one is to show you that nice thermal stratification that you get with displacement. This is exactly why displacement can be a good option for tall spaces. You can see that you're really only conditioning the occupied zone, and all that warm air goes up. You can actually see this nice thermal plume from the projector going directly up into the upper zone. And the other interesting thing I want to point out is that even though the grills on the windowsill are shooting the air up, because it's a low velocity, you could see it kind of cascades down into the space and begins to act kind of like a sidewall diffuser. So overall in cooling, this is actually working reasonably well. Our set point is about 75, so we're overcooled just a little bit. But in this case, we're actually meeting our comfort criteria in terms of your predicted mean vote. So it's nicely in that comfort range, as well as our head to foot temperature difference is also within ASHRAE guidelines. So let's now look at design B. So almost a little bit boring, but you could see that in this case, because we have the same CFM, the diffuser placement overall doesn't seem to be affecting the results too much. You're still getting comfortable temperatures in the space, except that your air distribution looks a little bit different. But overall, at least in cooling, they're providing a good, comfortable space. So a couple of different options for what you can do with the diffusers. So now if we want to look at them in a little bit more detail, so here I'm showing you streamlines, basically tracking the path of the air. Now these are going to show some differences in the designs. So you could see that, first of all, that I want to point out is that the need for having supply in the back. You could see that there's a bit of a dead zone in this widest part of the auditorium that the sidewall diffusers don't quite reach, and that's because they have to move the air through quite a few people and a lot of seats, so that air doesn't really travel quite as far as if it was just an empty space. So this is why in both cases it's a good idea to have some sort of air supply towards the back. One interesting thing that I want to point out is that size of the diffuser matters. So you could see that in design B, where you're using very tall diffusers, in this case they're kind of pressed for space and you needed a certain amount of CFM, you could see that the consequence of that is that because the diffuser is tall and that air is negatively buoyant, it tends to kind of fall down to the floor, which causes it to accelerate. So you could see in this case, you actually have higher velocities. So if you were married to design B and you didn't want to use the linear grills on the windowsills because you wanted the trough heaters instead, what you should do is either move these diffusers further away from the occupants, right, so that that velocity has time to dissipate, or again, if you can, maybe use more shorter diffusers. So they can be wide, that's not a problem. It's really the height that creates that kind of velocity in this case. So now if we want to look at temperature, this is right above the floor, design A and design B. And the reason I want to do this is to just really drive the point home of how far that cooling air moves. And again, why it's a good idea to have supply air from the back. So this is in any displacement system, ideally you have this pool of cool air near the floor that gets entrained then by the heat sources, right, which then raises that air up. So here you could see that for kind of these side sections closer to the sidewall diffusers, you have that nice pool of cool air. But as you start to get to the center and towards the back, that air is starting to be a little bit warmer. So in this case, this is not anything too much to be concerned about because we are supplying air from the back. So this kind of drives the point home that you know, when you have a certain width, in this case it's about 65 feet across, with this specific type of loading, it is a good idea to have some extra supply from the back just to make sure that you get nice even air coverage. So now we want to look at ventilation effectiveness. Again, this is looking first at cooling. We'll get into heating in a moment. So in this case, design A performs a little bit better. You get a higher ventilation effectiveness. However, in both cases, you could see that the audience area is very well ventilated. And actually, in both cases, the ventilation effectiveness is still higher than what you would see in the tables in standard 62.1. So 62.1, as you know, stipulates that displacement is about 1.2. So in this case, even, I guess, in the worst case in air quotes, you're still getting a ventilation effectiveness of 1.5. And the stage definitely not quite as well ventilated, but you could see that, especially in design A, just because that air supply is a lot more spread out, kind of locally right around those occupants, you are getting good ventilation effectiveness in their breathing zone. So now if we look at heating, A few things I want to point out. So first of all, we're still getting comfortable conditions. We're actually overheating just by a little bit. Our set point is about 70 degrees. If you recall, I didn't really highlight it in the input slide, but we're using a slightly warm temperature, supplier temperature in the displacement diffusers and heating. We're supplying 72-degree air, so just a little bit warmer than the space. Again, you don't want that to be too high because it is a displacement system. So technically, the air is doing some of the heating, and then the rest of it is being picked up by those trough heaters. So you could see this is design B, and I'll highlight this in a later slide as well. You can see that nice thermal plume from the trough heater, so it's nicely washing that window, conditioning the load right where that load occurs. And the other thing that I want to point out is that your stratification, although is lower than in cooling, which you would expect, right, because you don't have those concentrated heat sources in this case, you are still getting some thermal stratification, which is good. And thermal comfort, although is different from the cooling case, it's still within that comfort band stipulated by ASHRAE, standard 55. If we look at heating compared to cooling, so obviously you could see that the ventilation effectiveness is lower. And although the average is actually in this case below 1, I think we can very clearly see the reason as to why. So you see that even though it's lower in the audience area than in cooling, it's still actually kind of right around the 1.2 values in most of that space and nice and high. Really kind of what's affecting this average is this kind of zone of stagnant air around the stage. And I think the main reason, well, one reason for that is that the air supply is not quite as distributed because this is looking at design B. So distributing that to more diffusers would be a little bit better. And there's actually another reason for that as well, which I'm going to get into in the next slide, which again highlights the utility of using CFD. So the other reason is because that supply air, because that diffuser is really tall and very close to the perimeter, you could see that the air is actually being entrained into that thermal plume from the trough heaters. Again, because it's low velocity displacement air, it doesn't really, it's kind of easy for it to be entrained into other air currents. So in this case, just because the diffuser is tall and just because it's too close, it's actually robbing that area of that supply air. So in this case, the solution would be either shorter diffusers or at least to move those diffusers a little bit further away. You could see, however, in the rest of the space, although the air doesn't travel as far as in cooling, you could see that it's still doing a decent job kind of covering that central audience area, both from diffusers from the back and the ones from the side. So definitely some interesting little design tips that have come out of this example. So to summarize, I guess, this specific auditorium example, so in cooling, both designs provide good overall comfort and air quality. And the throw from the diffusers covers approximately 30 feet in cooling, give or take. We saw that supplying air from the back is a good idea to supplement the sidewalls. And that airflow from tall diffusers, I would say roughly anything taller than 3 feet, does tend to accelerate. So it doesn't mean it's outright bad. It just means you have to be careful with where you place it. We're also seeing that supplier travels a shorter distance at heating. And there's also less thermal stratification and a lower ventilation effectiveness in this case in heating than compared to cooling. And I guess since I'm still on the slides, just to conclude the webinar overall, we saw in the mixing examples that using a radial pattern diffuser in a patient room can cause discomfort at the patient bed. And then it is very important to minimize the temperature differential between the room air and the supply air. And it can create a comfortable environment in both heating and cooling applications, specifically if you're looking at tall spaces as well. We saw that displacement is a good option for conditioning tall spaces in both heating and cooling applications. And finally, since we did lean very heavily on CFD, we saw that CFD is a very useful tool that can be used to validate the design of these more complicated spaces before anything is built. All right, so that brings us to the conclusion of our webinar. Thank you everyone for listening on behalf of Sandrine and myself, and have a great day. Thank you.